let's explore a bit the infinite series from n equals 1 to infinity of 1 over n squared, which of course is equal to 1 plus 1/4, that's 1 over 2 squared, plus 1 over 3 squared, which is 1/9, plus 1/16, and it goes on and on and on forever. So there's a couple of things that we know about it. The first thing is all of the terms here are positive. So all of the terms here are positive. So they're all positive, and that they're decreasing. It looks like they're decreasing quite quickly here, from 1 to 1/4 to 1/9 to 1/16. And so they're quickly approaching 0, which makes us feel pretty good that this thing has a chance of converging. And because they're all positive, we know that this sum right over here, if it does converge, is going to be greater than 0. So the only reason why it wouldn't converge is if somehow it goes unbounded towards infinity, which we know if this was 1 over n, it would be unbounded towards infinity. So that's a possibility here. So if we could show that this is bounded, then that'll be a pretty good argument for why this thing right over here converges. Because the only reason why you could diverge is if you went to either positive infinity or negative infinity. We already know that this thing isn't going to go to negative infinity because it's all positive terms. Or you could diverge if this thing oscillates. But it's not going to oscillate because all of these terms are just adding to the sum. None of them are taking away, because none of these terms are negative. So let's see if we can make a good argument for why this sum right over here is bounded. And especially if we can come up with the bound, then that's a pretty good argument for this that this infinite series should converge. And the way that we're going to do that is we're going to explore a related function. So what I want to do is I want to explore f of x is equal to 1 over x squared. You could really view this right over here, 1 over n squared, as f of n, if I were to write it this way. So why is this interesting? Well, let's graph it. So that's the graph of y is equal to f of x. Y is equal to f of x. And notice this is a continuous positive decreasing function, especially over the interval that over the interval that I care about right over here. I guess we could say for positive values of x, it is a continuous positive decreasing function. And what's interesting is we can use this as really an underestimate for this area right over here. What do I mean by that? Well, 1, this first term right over here, you could view that as the area of this block right over here. That is f of n, or I guess you could say f of 1 high and 1 wide. So it's going to be 1 times 1 over 1 squared, or 1. This term, let me make sure I'm using different colors. This term right over here, that could represent the area of this block, which is 1/4 high and 1 wide. So it's going to have an area of 1/4. What could this one represent? Well, the area of the next block, if we're trying to estimate the area under the curve. And this might look familiar from when we first got exposed to the integral, or even before we got exposed to the integral when we were taking Riemann sums. So that right over here, that area is going to be equal to 1/9. So what's intriguing about this is we know how to find the exact area, or the exact area from 1 to infinity, from x equals 1 to infinity. So maybe we can use that somehow. We know what this area is right over here, which we can denote as the improper integral from 1 to infinity of f of x dx. We know what that is, and I'll figure out in a little bit. And if we know what this is, if we can figure out the value, that's going to be an upper bound for 1/4 plus 1/9 plus 1/16, on and on and on and on. And so that will allow us to essentially bound what this series evaluates to. And as we said earlier, that would be a very good argument for its convergence. So the whole point here, I'm not doing a rigorous proof, but really getting you the underlying conceptual understanding for a very popular test for convergence or divergence, which is called the integral test. Let me just write that down, just so you know what this is kind of the mental foundations for. So what do I mean here? So let me write this sum again. Let me write it a little bit different. So our original series from n equals 1 to infinity of 1 over n squared, it's going to be equal to this first block, the area of this first block, plus the area of all of the rest of the blocks, the 1/4 plus 1/9 plus 1/16, which we could write as the, let me do this in a new color, which we could write as the sum from n equals 2 to infinity of 1 over n squared. So I just kind of express this as the sum of this plus all of that stuff. Now what's interesting is that this what I just wrote in this blue notation, that's this block plus this block plus the next block, which is going to be less than this definite integral right over here. This definite integral, notice, it's an underestimate. It's always below the curve. So it's going to be less than that definite integral. So we can write that this thing is going to be less than 1 plus, instead of writing this, I'm going to write the definite integral. 1 plus the definite integral from 1 to infinity of 1 over x squared dx. Now, why is that useful? Well, we know how to evaluate this. And I encourage you to review the section on Khan Academy on improper integrals if this looks unfamiliar. But I'll evaluate this. I'll evaluate this down here. We know that this is the same thing as the limit as, I'm going to introduce a variable here, t approaches infinity of the definite integral from 1 to t of, and I'll just write this as x to the negative 2 dx, which is equal to the limit as t approaches infinity of, let's see, of negative x to the negative 1, or actually I could write that as negative 1 over x, negative 1 over x, and we're going to evaluate that as t and at 1, which is equal to the limit as t approaches infinity of negative 1 over t, and then minus negative 1 over 1, so that would just be plus 1. And as t approaches infinity, this term right over here is going to be 0, so this is just going to simplify to 1. So this whole thing evaluates to 1. So just like that, we were able to place an upper bound on this series. We're able to say that the series under question or in question, so the infinite sum from n equals 1 to infinity of 1 over n squared is going to be less than 1 plus 1, or it's going to be less than, let me do this in a new color, it's going to be less than 2. Or another way to think about it, it's going to be the 2 is this area, that's 1 right over there, plus this area right over here. So we're saying that this sum is going to be less than 2, so we have bounded it above. So we know it cannot go to positive infinity. Because all the terms are positive, it's definitely not going to go to negative infinity. And because all the terms are positive, we also know that this isn't going to oscillate between two different values. So this gives us a pretty good sense that this series converges. And the logic we just used here, to argue for why this converges, once again, not a rigorous proof, but this is the underlying logic of the integral test.